All right, now we can talk about how to actually solve one of these systems of equations that looks like this general form x prime equals ax, where x is a vector and a is a matrix of constant coefficients. To do this, we're going to do something familiar that we've done before, where we're going to assume a certain form of the solution. And this should remind you of what we did with second order equations, where we were looking for what kind of thing, when you take its derivative, has the same form. So without getting into too much detail, you have x over here, and then you have x prime, and so the question is what kind of thing, when you take its derivative, looks similar except with this extra constant thrown in perhaps. And so again, the details can get messy, but we'll assume that the solutions look like this, where we have e to the rt. R is some scalar, meaning not a vector. It's some constant value. And then u is a vector of constants. So in other words, we'd assume that x1 equals e to the rt times some constant, x2 equals e to the rt times another constant, and so on, like that. So if we assume that, then we can take that and see what conclusions we can draw. So then if that's true, x prime, the vector of constants wouldn't change anything, right? In the derivative, the constant multiples get carried along unchanged. So all that happens is that e to the rt becomes r e to the rt. So there's x prime. And if we substitute that into our matrix equation, we'd have r e to the rt times u equals a e to the rt times u. So then the e to the rt we can cancel from both sides because we know that's not 0. So we have ru equals au. And before we go any further, I'll mention that at the end of all this, we're going to get down to a conclusion, kind of like we did with the second order equations, that when you get to actually solving problems, all you really need is that final conclusion. All we're doing here is developing the theory behind it so that then you can jump straight to that point when it comes to actually solving examples. So to do this, if you don't follow all these steps, it's fine as long as you can take what we get at the end. But as we continue on, if we're solving this, we can say then if these are equal, then the difference between them has to be 0. Right? Now notice that the 0, I've put an arrow over it to indicate that's a 0 vector, meaning it's a vector of zeros, as many as you need. Right? So that's the 0 vector. And if that's true, we can factor out a u. But when we do this, I don't want to spend too much time talking about this because it can be a little quirky, but when we do this, we can't just write a minus r. Because if we did that, a is a matrix and r is a scalar, and so you can't subtract one from the other. So when you factor out this u, what you really want is you want like a times 1 essentially minus r times 1 essentially. But to make it a matrix, you multiply by a special matrix called the identity matrix. So just to mention briefly, this I is called the identity matrix, and the structure of it is ones along the diagonal and then zeros everywhere else. So 0, 0, 0, etc. All these are zeros. And if you practice with this a couple times, if you try to take examples, if you multiply any matrix by the right-sized identity, you get the same matrix you started with back again. So that's why it's called the identity. It's basically the matrix equivalent of 1. So we'll use that here and there as needed in these examples. So you should be familiar with the identity matrix. All right, so at that point, if u, we're assuming this vector of constants u is not 0, because if it's 0, then this whole thing would be 0, which isn't very interesting. So we're assuming u isn't 0, which means that this must equal 0. For all this to be true, it must be that a minus ri equals 0. equals the 0 matrix, I should be clear. So all that equals a 0 matrix. Now what we actually use to find R, we instead use the determinant of both sides. So we say the determinant of this side, we've talked about determinants before with Wronskian, the determinant of that has to equal 0. So that's what we use to actually solve for R. That's given on the formula sheet on the test. And that's what we're going to use as we actually solve R. So there's the determinant. And since we're only going to work with, when we actually solve examples, we're only going to work with 2x2 systems. The theory is the same for if you have a system of 3 equations or 4 equations or more, but we're just going to work with 2 for practice. So we can do 2x2 determinants as we've done with the Wronskian. So we don't need anything more complicated than knowing how to do that determinant. So when it comes to actually solving for R, what we're going to do is take our coefficient matrix A, and then we're going to take this general R that we don't know the value of yet, so we'll keep it as a variable, times I, and subtract it. So what that's going to turn into, you'll see this in an example in the next video, is basically in the matrix A, all of the entries along the diagonal are going to take whatever constant you have there and then subtract R. So we're going to have minus R, minus R, minus R along that diagonal. And then, well, we'll just have 2, but then we'll take that determinant and we'll have an equation involving R that we can solve. So you'll see that in an example, and we'll do that in the next video.